What is called fan out? Fan out equal one request triggers many child calls. Fan out on read expensive. Fan out on write scalable. So fan out just means that whenever you write something, it will trigger many child calls, and that's actually how you write two different followers. Twitter moved from old fan out on read 1000 lookups per timeline read, which has terrible tail latency, to new fan out on write 1000 inserts per new tweet. Reads become O1. Now each timeline read equal one chip lookup, so no tail latency amplification, no waiting first load because predictable performance. This is crucial for huge read heavy systems. Now let's connect to the networking side. Everything above happens inside the app or database layer, but the transport layer, TCP or UDP or QUIC, OS queues and kernel scheduling also affect tail latency. So before we discuss that, now in timeline of the customer, a read is a one chip lookup. So the ON or the time complexity became O1 because we use fan out on write. Therefore, no latency amplification, no waiting for slow D because predictable performance. This is crucial for huge read heavy systems. So whenever you have a lot of users that load a lot of timelines or read, or it's a huge read heavy, you would use a fan out read, which means that one write will trigger many child writes. Now let's connect this to our previous discussion about TCP IP, OS, kernel scheduling, etc. How TCP increases tail latency? TCP is reliable and ordered. That sounds good, but has side effects. TCP HOL, head of line blocking. So the head of line blocking that we discussed, which has queues, because TCP is unordered protocol, therefore it must follow some kind of queues. If one packet is lost, receiver cannot deliver any later packets to up. It must wait for retransmission. All buffer data is blocked. Tail latency spike. So tail latency is also connected to this head of line blocking, which has a queue, because before it receive the, let's say, second data, if the first data were blocked, it will need to retransmit that first data first before it can accept the second data. So all buffer data is blocked. In video or timelines, this causes random stalls. TCP congestion controls stalls. If congestion is detected, TCP slow down, reduces congestion window, increases RTT, increases jitter. Again, tail latency events. Kernel send or receive queues. TCP uses OS kernel buffers. When queues fill, drops, it will drop it. Background processes compete in scheduling. Random spike in processing time. This is also increases tail latency. So for queues or for kernel, the TCP that handle this, the OS that handle this TCP also must deal with the kernel buffer that the TCP encountered. So when queues fill up, it will drop it on the kernel side. Take note, it's not in TCP. And background processes compete in scheduling because there's a lot of queue that is waiting to be processed by the kernel. So a lot of processes or background processes compete in scheduling. Random spikes in processing time. So some process will have a lot of processing time compared to others, which in the OS case, As we saw in a multi-feedback queue, some process actually take a large proportion of time compared to other process. This is also called tail latency. But in the OS side, how UDP behaves better sometimes. UDP equal no retransmissions, no ordering. This means no head of line blocking. App chooses retransmission strategy, lower transport tail latency. So because UDP does not do what TCP does, which it retransmit and wait for the next queue, it allows the user space to execute or implement the and implement the sorry about that, and implement the TC or the retransmission on the user space. Also, it doesn't affect the kernel as TCP would have affected it. App chooses retransmission strategy, lower transport tail latency, but UDP is too raw for complex apps. So not all apps use this because it may not satisfy their application requirements. How QUIC dramatically reduces tail latency? QUIC was invented because companies like Google, Twitter, Facebook were getting destroyed by TCP's tail latency. QUIC benefits. A. Eliminates TCP head of line blocking. So just as UDP does, since QUIC use UDP, it eliminates head of line blocking as well. QUIC streams are independent. If one packet is lost on stream A, stream B continues normally. This is a massive reduction in tail latency. User space talk, faster, upgradable. QUIC runs in user space. It avoids kernel scheduling delays, allows faster congestion control. So unlike in TCP, which if you have congestion, it will reduce the congestion window, the RTT, and the jitter. And it's a tail latency event again. Custom retransmissions, so the user space chose to retransmit it, kind of like the by default configuration of TCP. Better recovery strategies, fewer system call because it's in the user space. So remember, whenever there's always a cost in calling the system or trapping into the kernel. So here, since it's a user space, we don't need to do a system calls. Connection migration or not rebinding. QUIC's connection ID allows laptop moves to new Wi-Fi. So that's another benefit, not mapping change. That's why when you change from mobile data to Wi-Fi, your YouTube video weren't affected. IP changes without losing connection prevents reconnection delays. 0 RTT and 1 to RTT handshakes. So again, it's kind of like in the congestion control benefits. QUIC reduces handshake latency drastically. So you don't need the handshake, just like with TCP, which actually cause the congestion control. Fewer round-trip operations, fewer chances to hit high latency. How microservices and RPC parallelism tie into tail latency. Modern architectures use REST, gRPC, TRIF, GraphQL federated resolvers. These often make parallel backend calls per request. Example in a microservice system, front end, when you request timeline service, it also has a child call of user service, follow service, tweet service, media service, ad service, abuse service. If any of these are slow, UI is slow. That's tail latency amplification again in the RPC layer. So RPC is what you see on the front end. and these often make parallel backend calls per request, just like the modern UI today, or a single page application or server side rendering. They usually have parent call that trigger a lot of child calls that allows your app to be loaded at once instead of the previous PHP way which you send a request to the server each call from the front end. That's not how it works anymore. Quick helps reduce that because Quick reduces transport latency variance, prevents delay due to packet drops, so it reduces transport because it is using UDP, prevents delays due to packet drops, so it doesn't need to be in queue just like TCP. It supports multiplex streams, so the streams, it will be important later when we talk about how do we actually implement how Twitter actually implement that in cloud. Avoids TCP blocking. How does all connect to your earlier learning? So you studied how UDP sends 1 datagram per write, how Quick uses UDP but better, socket buffers, ephemeral ports, port mapping, how OS kernel handles routing and sockets. Now you're seeing all those low-level networking behaviors create variance. Variance creates tail latency. Tail latency breaks read-heavy architectures. So because Twitter and Facebook is a read-heavy architecture, tail latency break that. So all of this low-level networking in UDP, in transport layer, in user space, in socket, ephemeral ports, port mapping, how OS kernel handles routing and socket, create variance. Variance create tail latency. So this variance actually affect how the delay affect each layer, forcing systems like Twitter, Facebook, TikTok to shift from read to write because tail latency dominates real-world distributed systems. Final mental model. First, application layer, fan out on read, tail latency amplifies, slow timelines. Fan out on write, fast timelines. Second, RPC or microservices layer, more parallel calls equal higher chance of hitting a slow one. So in application layer, whenever you're requesting for a timeline in the newsfeed, a fan out on write equals fast timelines. For RPC or microservices, more parallel calls. So let's say your front end call or has a lot of child calls, it equates to higher chance of hitting a slow one. In transport layer, for TCP, you have head of line blocking, retransmission, which also means tail latency. For UDP, no guarantees means less blocking, so UDP is better in TCP. Quick, best of both, no head of line blocking. It allows streams and allow for fast recovery in case it lost the packet. Kernel layer, queues, scheduling, buffer pressure, tail latency spikes. Everything stacks on top of each other. Multiplicative effect, so that's what it called. So the queues, there's also queues in the kernel. There's also scheduling that also were affected by the TCP head of line blocking, which also provide or produce tail latency, and there's also a buffer pressure. Quick plus fan out on write plus microservices optimization all work together to fight the same enemy, tail latency. So here is actually how we apply this in real world. How real AWS systems avoid fan out on read plus tail latency. Companies on AWS or Google Cloud avoid tail latency using 5 real-world techniques. Technique 1. Move work from read to write, fan out write, just like Twitter. Why? Reads are 100x to 1000x more frequent than writes. So instead of read timeline to query 500 followees, they do write tweet, copy it into 500 follower timelines. Think of AWS architecture. Kinesis or Kafka streams distribute events. So this is the streams that Quick provide that I'm talking about in AWS. It's in Kafka streams. It distribute events. Lambda or ECS or K8's consumers fan out with timeline caches. So this is how you fan out the parent that has child calls, and it also how you provide the caches. DynamoDB, Redis, Aerospike per user timeline store. So this is how you store the user timeline. So how you separate that timeline. So each timeline read one chip O1 lookup. So these are the architecture that allows this one O1 lookup, but also came from the section we discussed earlier. This eliminates tail latency amplification from 500 queries to 500 services, 500 random slow nodes, 500 network round trips. What AWS service combination replaces fan out on read? So here is the services that AWS can that you can use in AWS to replace fan out on read or to create a fan out on write. Option A, modern. We have API gateway to Lambda, to Kinesis stream, to Lambda consumers, to DynamoDB. Option B, Twitter scale. You can start with Kafka to fan out workers to Redis cluster on or DynamoDB. Option C, for TikTok or Meta, we have Kafka. So it's like the same with Twitter scale. To Flink real-time processing, to shared timeline DB. How this relates to microservices, your earlier example. Fan out on read, bad. Because for timeline service, you also have this child service, which is tweet service, user service, follow service, media service, ad service, abuse service, tons of parallel RPC calls, tail latency amplification. Fan out on write, good. When a tweet is posted, tweet service publishes event to Kafka. Fan out workers push copy into timeline DB. Timeline service now reads one small record. So a tweet service like this in a Twitter scale, it published that to Kafka or publish event to Kafka when a influencer posted a tweet. Then a fan out worker push copy into timeline DB. So here the timeline DB is actually in Redis cluster or DynamoDB. Then a timeline service now reads one small record instead of multiplying that in multiple fan out on reads. Why this prevents tail latency? Because instead of one timeline read equal 1000 slow microservice RPCs, you get one timeline read equal one fast key value lookup. So the change the algorithm from ON to kind of like a hash table. That's why it has a one fast key value lookup. Remember, hash table has a key, it has this properties, a key value, so almost no tail latency. AWS also helps reduce tail latency with these techniques. First, caching layers, CloudFront, Elastic Cache, Redis. So that's how we store the timeline earlier in scaling Twitter. DynamoDB Accelerator, DAX, client-side caching. Second, replication plus sharding, multiple database copies reduce read hotspots. So for example, you have this updated, you have this two database and one is updated, you would show that database to the user, the most updated one, and discard the second database. And all of the read requests to that second database will be discarded or logged in the backend. Third, hedge request, send two requests to two replicas. Use the faster. So in hedge request, you would send two requests to two replicas and use the faster. So this is actually what I'm saying earlier. It's in hedge request. It's not actually in replication plus sharding. Google invented this. AWS users copy it. Now it actually started from Google Cloud. Now let's connect to percentile monitoring. HDR histogram, T-digest. To detect T latency, P99 spikes, P99.9 jitter. So this is actually the P9, the jitter we saw in TCP congestion, along with the I forgot that RTT. Yeah, fan out delays, network congestion effects. System use approximate percentile histograms. HDR histogram, track latency in log scale buckets. So there's actually a service in S3 that also tracks this bucket type. Extremely fast, perfect for microservices, can merge histograms from 10,000 servers. So this code or library of HDR histogram actually track a large data, and it's fast because it only approximate, and it also use lower memory. There's also a library T-digest. It maintains compact clusters, excellent for high percentiles, P99, P99.9. So if you want more accurate, this library is better. It's also better for a compact clusters, good for distributed aggregation. Why not keep raw request times? Too slow, too memory heavy. So if you track all of the data without approximating or using this library, it's too memory consuming, too expensive to sort, too slow. These histograms allow real-time monitoring. Also, it's hard to search. It's hard to categorize in a lot of memory, in real-world memory. Now, which microservice is this histogram allow real-time monitoring of? Which microservice is causing tail latency right now? This is crucial in AWS microservice architecture. So it allows you to see which timeline or even the child service like tweet service, timeline, what services is that? Follow service, media service. It will allows you to see what services are causing the spike, therefore allow you to better resolve the issue. CDNs. Why edge networks matter for tail latency? CDNs reduce tail latency by, first, moving data closer to users. The farther the data travels, the greater RTT, so it's linked to the congestion control of TCP. So the farther data, the greater that RTT. The greater the packet loss, which is related to UDP, the queuing delay, which is related to TCP, and the congestion. Now CDNs, CloudFront, Akamai, YouTube Edge, Netflix Open Connect reduce TCP retransmission delay. It reduced that using the RTT. BGP routing slowness, which is the NAT, related to NAT we discussed in the previous video. Cross-region jitter, packet loss, causes TCP or quick delays. This dramatically lowers tail latency. How YouTube video chunking avoids tail latency. YouTube doesn't stream one gigantic file. It delivers video in small independent chunks, 2 to 4 seconds, using Dash. Why? So this is actually the language for that send video to you, to your YouTube app via network or via internet connection. Why? Because first, small chunks equal fewer tail latency events. So that's also related to tail latency, because if you just provide that 2 to 4 seconds video at a time, it allows you to avoid these tail latency events, and therefore allow you to avoid any unexpected crashes. If one 4-second chunk is low, YouTube can fetch a different bitrate or try another CDN server. So even if just 1 4-second is low, YouTube can then now fetch a different bitrate. So bitrate is different resolution, a lower quality, etc. Try another CDN server, or retry quickly, or prefetch ahead. If YouTube stream the whole 2-hour video through a single TCP stream, a single packet loss equals to head of line blocking, random spikes, freeze, tail latency, entire video stalls, Wi-Fi jitter, ruin stream. So instead, they use those chunks in order to avoid or to prepare for this all edge cases. Even the Wi-Fi jitter could ruin the stream. So chunking plus quick avoids this. YouTube's real architecture to avoid tail latency. First, client chooses nearest CDN cache via DNS plus quick metrics. So again, just like in the previous video, DNS still the first one you use to choose the nearest CDN. Plus quick, it also uses a quick metrics, which is a combination that kinda beast, because it allows to resolve this tail latency in real world, even with the Wi-Fi jitter. Second, client fetches chunks in parallel. Third, adaptive bitrate, ABR. If tail latency increases, chooses lower bitrate. If tail latency decreases, increase bitrate. Fourth, quick helps. No TCP head of line blocking, faster recovery. Independent streams, lower variance. Fifth, aggressive prefetching. Clients loads 1 to 2 future chunks in advance. So quick helps with faster recovery as well in independent stream and lower variance. Now final connection map, everything together. We have user connected via DNS to CDN Edge, CloudFront or YouTube CDN, then video chunk along with quick, then work done on write Kafka to fan out. So for timeline, after YouTube CDN or after the CDN, if we choose timeline read along with Redis or Dynamo, it will reduce fan out on read, and then it will connect to lower tail latency application. It connects to quick remove transport layer HOL plus reduce jitter, and it will connect to CDN's reduce packet loss and network tail latency, and it will connect to histogram HDRT digest detect P99/P99.9 spikes. So after CDN, if we choose social feed connected to ABR plus fan out, then it will connect to work done on write, tweets, post, then Flink to materialize views. This is how real systems scale. Write becomes expensive, reads become fast, RPC fan out minimize, quick reduces network tail latency, CDNs reduce global routing delays, Chunking avoid long stalls. Histogram detects spikes. Replicas plus hedge requests reduce variance. This is the industry standard architecture today.